So I decided to do something so perfectly ridiculous I gotta share it. This is this whole jumble is a regulated power supply. Except for this part, that's the load. But the rest of it is pretty much a power supply plus extra shit. You'll notice there are no semiconductors except for some rectifiers. No transistors, no tubes, nothing like that. It has negative feedback, and it regulates magnetically. The whole thing is magnetic, and so it's using a saturable reactor to do this. And it's a mess because I've just been kind of fuzzling my way through it as I go, but I could clean it all up and make it orderly. Many of the things here are sort of extra to they're superfluous to the explanation. The variacs don't really need to be here, but they're there so I can get an idea, a feel for how things work. So just to start off with, that's a regular power transformer. It's 120 mains going in and it's 80 volts going out. I've got the variac on that so I can do line regulation tests. This guy, anyone who's familiar with this stuff will recognize immediately as a saturable reactor. You see the three windings, and you'll notice that if you look at the back, the two outer windings are in parallel, and they're in anti-parallel. So they do not interact really through the core. I mean, there's a little tiny bit of interaction due to imperfections, but they cancel. But the center winding, of course, is going to be able to see both of them. Yet, because they're in parallel, and they're both the same number of turns and the same voltage on them, the center winding doesn't see any AC back from those because it cancels in the center of the core. You know, one magnetic field is going to be pointing through the core this way, while the other one is pointing through the core that way. So you've got, say, so many Tesla going this way and so many Tesla coming back. If it's equal, they cancel. There's no net field in the core due to what they would say is the AC windings. So, and then this, of course, is just a choke. It's just a big honking inductor. I've been playing with the shims to change the inductance and the saturation point. And so what's going on when you do something like this is the mains comes in, it goes in series through the reactor, and then the output from that is fed to a bridge rectifier, and then off to whatever kind of output filter you want to have. So the inductor is superfluous to this being a saturable reactor or mag amp type power supply. It's there as a means of properly filtering the output. Because if you put this straight onto a cap and you've got a saturable reactor, it's like switching a transistor into a capacitor or switching a triac. This is much closer to switching a triac. In fact, it is a type of phase chopper power supply, effectively. I'll get into that in a minute. But yeah, you really want inductive loads for hard switching switches. Otherwise, you get massive current pulses that are just useless. It's got terrible power factor, heats up the wires, pisses off the EMC people. It spits out all sorts of harmonics, and it's loud, and it's just not a good thing. So we use inductance, which sucks because inductors are shit. They have to be huge to store any energy, and they are lossy and heavy, and they make noise. Capacitors are way better. This little capacitor here can store a lot more energy than this inductor before it runs into its limits, essentially. In a capacitor, our limit is voltage, and in an inductor, it's current. And you'll see on any inductor, here we have 30 amp choke. So if I have the original shim thickness in here, this core starts to saturate enough that we care, around 30 amps, and then it starts to become kind of useless. And I wanted to give up a bit of that limit. It's probably going to saturate around 15 amps now, but I'm getting double the inductance, so kind of handy. So anyway, yeah, so we've got power in series with a saturable reactor through a bridge rectifier, and then after that things start to look more normal. You've got an inductor, and hiding in here there's a capacitor across this as well. So it's like an LC filter off of a regulator, or of a rectified power supply, and then a load resistor. This is 6 ohms all the way from top to bottom, and you can see there's a tap not quite in the middle. It's like 3.5 ohms from the top, so it's just two different currents I can draw. And what was I going to say? So the way the saturable reactor works, this is going back to the saturation thing, so you start to get a certain amount of current through the windings, and you get so much magnetomotive force off of that going into the core, and eventually you reach a point where you keep applying more force and the core will no longer confine a magnetic field, and it starts to spit out into space. And the permeability drops, the inductance drops down to what the coil would look like if it was not in a core. It would just be the same as if it was in air or in space. And this is not a hard switch, like an instantaneous change. It's a slow, gradual thing. Depending on the material the core is made out of, it can be very gradual, or it can be relatively abrupt. In some materials, many ferrites, it is very abrupt. And that's a trade-off that we make, a sacrifice we make, because of the extremely high permeability that they give us before they get there. Whereas this stuff like magnetic steel, electrical steel and whatever, it saturates hard, sort of, but it's pretty mushy. You can push them pretty hard, you're just going to end up generating heat and noise, but you're not going to hit a wall. But the reason we have these reactors is sort of we're using saturation as a switch. And what we're doing is we are basically, as I said, this is in series with the mains. On every half cycle, either half of the core is getting saturated at a given point, and that point can be biased dependent on a DC current that's applied to this center winding. And you notice it's got a lot of turns. It's fairly thick wire. I think it's like 18 gauge, but I mean there's a lot of turns in there, so it doesn't take much current to develop a pretty strong magnetic field. And the idea is you can bias both halves of the core closer to saturation as you wish. All the way, you can turn the control winding all the way up till the whole fucking thing is saturated before you've even begun to apply input. And in which case, if it's saturated, that's another way of saying it doesn't have any inductance left. So it starts to approach what would look like a wire. It'll conduct a lot of current. But if I start to pull back on this bias in the core, standing sort of steady magnetic field that I've applied, then I get back some inductance. And so if you were to look at the input and output off this, the voltage drop across this, it would start to look like it was clipping the tops of the waveforms off. So you're getting inductance up to a certain amount of field, and then it runs out of inductance, and it starts to really pass current, and the voltage stops rising. And we vary that by changing the DC. So that's what a magnetic amplifier does. And people sort of differentiate between, magnetic amplifier, saturable core reactor. A saturable core reactor is something you use in magnetic amplifiers. We'd never really think of a reactor as an amplifier. It doesn't really become an amplifier until you've applied it in circuit. No more than one considers a transistor to be an amplifier on its own. It's not really at all. It's in fact, the voltage gain of a transistor is given by the load resistance, not by the transistor itself, technically. There's a bit of a caveat there, but I won't go into that. So knowing this, keeping this all in mind, we can imagine, okay, well, hey, we can vary the RMS voltage that's coming out. There's going to be a lot of distortion. And again, this is like a phase chopper circuit you'd use for dimming the lights or turning a heater up and down. We know those are the same way. The RMS voltage is controlled in a certain way, but the peak voltage is not necessarily changing until we start to move past 90 degrees phase, and then we start to move past the peaks of the waves. But we don't really care. We sort of accept that distortion, all those harsh edges and harmonics, because it's a cheap, effective way to control the average output, what we care about, what a resistive load would care about, without getting into anything lossy. If it's hard switching, then it's not really giving up any heat. Before that came around, before semiconductor, 4-layer devices like SCRs and triacs and bilateral trigger diodes, all that stuff, we call them thyristors, got going, we used stuff like this, saturable reactors. They were used in a lot of stuff for regulating, switching, and in some computers and they're actually used for logic circuitry, all magnetic. So we can, yeah, we're just thinking, okay, well, we can vary a very high current load. This whole puppy here will do around 60 volts at 30 amps output, which is quite a bit. And I can vary that pretty well all the way from 0 to max by changing the current on this control winding, using up only about 12 volts and maybe a tenth of that in amps. So we're only using, 10 watts or whatever to control, like almost 1,000 watts, or probably more than 1,000 watts. So there's a lot of power gain, like a hell of a lot of power gain here, and that's why we want it. It's amplification. But if we have power gain, it means we can apply negative feedback and get self-regulation. It also means we can apply positive feedback and get an oscillator. And I am going to make an oscillator out of this later and show what that looks like. You can do all sorts, anything you can make an amplifier out of, you can make a regulated supply, an oscillator, and so on. The principal components of pretty well all electronic stuff. So to apply negative feedback to this is where I got kind of interesting. I started by taking a sample of the output voltage it's developing across the load and simply adding an offset to it. I started with a lead acid battery, 12 volts. Okay, the idea being, before I fire this up, there's 12 volts applied in series between the load and the control winding. So, whatever the resistances are, it works out. A bit of it is eaten up in the load and a bit in the control winding. But it basically starts the thing off kind of wanting to just max itself out. But as the output increases in voltage, it starts to subtract from the battery voltage until eventually there's almost no voltage across the control winding. And that is how you would get negative feedback. And that worked really well. I think that got me like better than 10% regulation, load and line, which I wasn't expecting. It can never be perfect because there are losses. The gain is always a little less than 1. But I added another twist here to get more gain. I've taken a variac and an isolating, just whatever transformer in order to do the isolation. And that is taking a sample of the output pre-rectification, so before the choke and all that stuff, and it's passing it through. It's got to be through isolation, otherwise I'm going to short some stuff out here. And it's passing that back and subtracting some feedback off of the output circuit that I already had. And it is actually, I've got a variable power supply over there kind of taking over for the battery, so I could change the output voltage. But changing the variac changes the amount of negative feedback because it's changing the gain of the whole system as if it were an amplifier. We could look at it as if saying it's changing the system gain, or we could look at it as saying that we're applying more or less feedback. The effect is the same whichever way you look at it. But I could get it now. I can crank up the feedback to the point where the regulation is very tight. And this is where I'm going to show you what I've got. We've got, where are we at? 11.7-ish volts, and that's dropped into 3.5 ohms or something like that. So there's a decent little bit of juice going along. And my input voltage is right on 120, more or less. So I'm going to vary this. I don't know if you can see the meter and the variac at the same time. And you can see the scope too. I'll try to make it so you can see the scope. For those who are curious, the top waveform is the voltage dropped across the output filter inductor, and the lower waveform is the current in the series circuit between the mains and the load. So I wanted to see, basically the current is showing me kind of what the saturation looks like, and you can see exactly the effect there. The current doesn't really start to rise until after a little while, then it really rises fast and comes back down, and then it sort of slows as it crosses the zero crossing. That's what my reactor is doing for me, is it sort of waits at a low current up until the things get moving a bit, and then it starts to really conduct. And as you can see, the pulses of current in the output filter inductor are rectified, so they both point in the same direction, but they coincide with the saturation of the reactor. So anyway, back to this, so you can see, watch everything. 11.7 volts output and 120 in. I'm going to go down to 100. And you can see it's very slow. There's a lot of inductance here, so things are going to change pretty slowly. But as you can see, the output voltage is only 10.8 now. What was it? It was 11.7, so it drops by maybe a volt, even though we're changing the output about 10 volts. And then if I go up to 130, 11, 12 or whatever, so from 120 to 30, it's changing very little. So it's showing me that there's a fair bit of non-linearity going on here, but that's fine. Let's try increasing the resistance in the load. Now here's a fun thing. If I disconnect this, you'd expect this to like really overshoot, but it doesn't go very far. You know, for a modern power supply that would be unacceptable, but if I had no feedback applied on this and the saturable reactor was at the same bias current, I mean, that would have shot up to around 80, or actually I think I had it was shooting up to about 100 volts. So we'll put almost double the resistance on, and there she goes, 12.5 volts on 120. So if I go down to 110, I mean, that only drops what, from 12, we'll say 12.3. If we go back up to 120, 12.7. So 400 millivolts, that's it. Go up to 130, hardly changes at all. I can go down a fair bit. So I'm at 80 volts on the mains now, still getting 10.9 in the output. So that's pretty good. I mean, go down to, okay, we're at 60 volts, 9.9, and then back up to 120. So yeah, you know, not great as far as, you know, a modern semiconductor or even a vacuum tube regulated supply, but for a whole bunch of iron and copper, it's pretty good. I can vary the, you can see we're dropping about 40 volts into it, and then the difference is being subtracted by the gain increase circuit, and then the output is, you know, 13 volts or whatever. So if I'm going to drop the thing from 40, down to, say, 20. So now we're at about 6.6, and I expect the regulation to be a little tighter now. So if I put 120 mains going in, put a 110, yeah, go down to 100. Let's go down to like 50 volts. Yeah, so we've lost like 1.4 volts or whatever. Let's go up to 140 going into this. So yeah, not bad at all. Again, I'll try loading it more heavily. We'll go down nearly half in resistance. So that's going from, we're basically doubling the current, and yet the voltage is changing by half a volt. Not bad at all. And at the higher load, the regulation is probably a little worse. So I'll go from 120 down to 50. 4.5, go up to 80, 100, 120, 140. Pretty good, and it's not too slow. I mean, it's slow, but I'll zip this knob along as quick as I can. Just go down to about maybe 80. And we'll go all the way up to 120, and I'll try to do it quick. If you're watching the scope, you can kind of see, watch it kind of mush back to the regulated voltage. And like I said, the reason it's so slow is because the control windings on this have a heck of a lot of turns. So there's a ton of inductance. You really have to overshoot hard on the control voltage to get the bias current to really change the magnetic field in this core. And there's a bit of remnants going on probably, so yes, it can be a little slow. You can speed that up if you use a means of increasing dynamic range of the bias circuit. And also it's going to be kind of unidirectional. It's easier for this thing to increase the field than it is to decrease it, because in order to decrease it, you really would have to pull the bias voltage on that winding reverse of whatever it is. It doesn't care what polarity of bias voltage you're using. If you went positive or negative on this winding, both will actually have the exact same effect. It's going to reverse the phase of the output. But other than that, if you want to discharge that magnetic field, you're going to have to pull voltseconds out, and the only way to do that is to invert the voltage. It's just inductor theory. Same old thing we see anytime. So that's about all I've got to say on this. I could go on and on, but I've already been at it for 20 minutes, so I'm going to quit. But if anybody has any questions, let me know. And I'll probably do a few more experiments with this stuff. Like I said, I want to make it oscillate to show what that looks like. And I've got a bunch of smaller stuff that'll work at higher frequency, and I've got some nice sinusoidal, I think they're 40 kilohertz power supplies that do 12 volts at like 20 amps or something like that. It's quite a decent bit of current, and they're meant for track lighting. So my thing is, I might try to stick those on too. I mean, I've got another Saturable Reactor set that is done in, I think it's ferrite, sitting over kind of on the shelf there. That thing will go fast enough to do, not full band audio obviously, but you could run a subwoofer off of that just fine. So I'll probably do a demo of a magnetic audio amplifier, and I don't mean like the quote-unquote magnetic Carver amps, which are not magnetic at all. They're regular solid-state amp with literally a light dimmer circuit driving the power supply transformer. It does work. It increases the efficiency of the amp. It lets them get a lot more output power for a given set of output devices, but there's not really anything magnetic going on. I'll make something that is actually truly a magnetic amplifier. It's not using any solid-state devices or tubes to affect the power gain at all. So yeah, that's enough for now.